Assalamualaikum warahmatullahi wabarakatuh. My name is Nofatni Adriana binti Muhammad Zainuddin, and I'm here to solve a question. So the question is, find a solution to the partial differential equation. So the equation that's given is du over dt is equal to k d square u over dx square. So and here we have three boundary conditions, which is u at 0 is equal to fx, u negative lt is equal to ult, and du over dx negative lt is equal to du over dx lt. So first thing we will rewrite them so that it will be easier for us to see. So we will write them as u negative lt minus ult is equal to 0, and du over dx negative lt minus du over dx lt is equal to 0. So this is, as you know, this is the assumption that we use in separable variable method, which is u x t is equal to vs gt. And this is the two ordinary differential equation that we will need to solve, which is dg over dt is equal to minus k lambda g, and d square v over ds square is equal to minus lambda v. So this is when we inserting this assumption into the boundary condition, and we will get gt v negative l minus gt vl is equal to gt v minus negative l minus vl is equal to 0, and gt dv over dx negative l minus gt dv over dx L is equal to gt dv over dx negative L minus dv over dxl is equal to 0. And we get non-trivial solution if we do like this, and like this. V negative L minus VL is equal to 0. V negative L is equal to VL. And dV over dx negative L minus dV over dxl is equal to 0. dV over dx is negative L is equal to dV over dxl. So here we will get after applying separation variable this. So as you can see here, lambda is an unknown value. Hence, we have three cases for us to consider for lambda. So the first is lambda is more than 0. The general solution to the differential equation is Vx is equal to C1 cos square root lambda x plus C2 sine square root lambda x. So first we will applying the first boundary conditions, and it will become like this: C1 cos negative L square root lambda plus C2 sine negative L square root lambda is equal to C1 cos neg L square root lambda plus C2 sine L square root lambda, and we will get 0 is equal to 2C2 sine L square root lambda. At this stage, we can't really say either C2 or sine could be 0, so we will apply the second boundary condition, and we will get 2 square root lambda C1 sine L square root lambda is equal to 0. So notice that we get something similar between this and this, and the eigenvalues that we get for this problem is this. This is the eigenvalue. Lambda n is equal to, in bracket, n pi L over L square. And this is the eigenfunctions corresponding to the eigenvalue, to these eigenvalues. This is the eigenfunction that we get. So for the second case is lambda is equal to 0. The general solution for this case is Vx is equal to C1 plus C2x. So we will apply the first boundary and we will get C1 plus C2 negative L is equal to C1 plus C2L, and we will get 2L C2 is equal to 0. C2 is equal to 0. So the general solution is then Vx is equal to C1, and it will satisfy the second boundary condition. Therefore, lambda is equal to 0 is uh, is an eigenvalue for this BVP, and the eigenfunctions for this problem is Vx equal to 1. So next is the third cases, which is lambda less than 0. So the general solution for these cases is Vx is equal to C1 cos square root negative lambda x plus C2 sin square root negative lambda x. So first we will apply the first boundary condition, which is C1 cos negative L square root negative lambda plus C2 sin negative L square root negative lambda is equal to C1 cos L square root negative lambda plus C2 sin L square root negative lambda, and we will get 2C2 sin L negative square root negative lambda is equal to 0. So now in this case, we assuming lambda is less than 0. So L square root negative lambda can't be 0. And also sin L square root negative lambda also can't be 0. So we must have C2 equal to 0. So we will apply second boundary condition, and we will get 2 square root negative lambda C1 sin L square root negative lambda is equal to 0. C1 is equal to 0. So no. Summarizing up, then we have the following sets of eigenvalues and eigenfunctions. So this is the problem, the type problem, which is identical to the two we have already worked. So we have gt of is equal to c e the power of minus k n s over l square t, and this is the two differential possible product solution that will satisfy the partial differential equation and the boundary condition. These two differential equations, differential possible product, and the solution for this partial differential equation is this. And if we apply the initial condition to this, we will get u x0 is equal to fx is and this is equal to n equal to 0 up to infinity a n cos n by x over l plus n equal to 1 up to infinity bn sine n pi x over l. So the coefficients are given are this. So that's all from me. Thank you.